We've seen that a connected object can include an applied force on an angle. As well, a connected object can include an incline, like this one does. On the one hand, this one's not too bad because it doesn't have any friction, but we'll talk through how to do it. And if you come across one of these in the future that does have friction, it's not a big deal to add that in. As always, going to draw free body diagrams and analyze them. Move on to the next object, get two equations, two unknowns, and crank it out. I'm going to start with the hanging mass. There are two forces going on. Gonna go ahead of myself. There are two forces acting on the hanging mass. The string is pulling it up, and gravity's pulling it down. Setting up F net equals ma. Since the 4 kilogram is going to go down, I'm going to make that the positive force. And sub in, we know that gravity is mg, Ft is our negative force, equals ma. Doing a little bit of work in my head, 4 times 9.8 is 39.2 minus Ft equals 4a. That's as far as I can go with the 4 kilogram. Switching to the 2 kilogram, it's on an incline. We tackled that earlier. Free body diagram, the string is pulling it parallel to the incline up the hill. Normal is perpendicular to the hill. There's no friction. If there was friction in this case, it would be downhill. And then we've got gravity pointing straight down. As we talked about when we did inclines, it's always important to think about the component it's accelerating in. In this question, the one on the incline is accelerating up the hill. So I'm going to look at components that are perpendicular to the hill and parallel to the hill. When we set it up, the angle of the incline should have been drawn down here. The same angle shows in our component triangle up here. Since there's no coefficient of friction, we don't really need it, but just for practice, normal is balanced by what I call the perpendicular component of gravity, and that's related to the cosine. We don't really need it this time, but if we did, if you come across a question later, that perpendicular component's related to cosine. What we do need is the parallel component. We're going to set up F net equals ma. The force that's winning, that's going to make it move, is the tension. The force that it's got to beat is the component of gravity. That's this component down here, Fg parallel. That's going to be equal to ma. I don't know Ft, but I know Fg parallel. It's opposite the angle, so that's related to the sine. Now if I sub things in, I can't do anything with Ft. I'm stuck with that. The mass was 2, so I have 2 times 9.8 times the sine of 30. Sine of 30 is a half, so doing that in my head, or you could verify on a calculator, that middle term turns into 9.8, and that's equal to 2a. That's my second equation. If there was friction, I'd have to do a little bit of work. It would be a subtractive thing. It'd be mu times Fn. I know that the Fn is mg cos theta. It wouldn't add a lot. It would just be another term in the equation that I'd combine with the 9.8. To finish this off, equation 1 was 39.2. Take away Ft equals 4a. Equation 2 was positive Ft, but negative 9.8. And that was equal to 2a. As expected, that connecting force should be positive on one object and negative on the other. When we clean this one up, 39 minus 9.8, we're getting 29.4. And that's equal to 6a. I actually didn't crank this out on my calculator, but the answer is going to be 29.4 divided by 6, which I don't have in front of me. Kind of goofed up when I was prepping, but it's close to 30 over 6, which is going to be pretty close to 5. I'll let you double check, but whatever 29.4 over 6 is, that's going to be our acceleration. So even though it looked a little bit different, it had an incline. We're going to take those skills we learned when we learned how to solve for inclines, the skills for connected objects, free body diagrams, 2 equations, 2 unknowns, and we can solve pretty much any